class, we'll talk about the sensitivity analysis. So usually, after we solve a linear programming problem using the simplex method or the dual simplex method, we want to conduct the post-optimality analysis. In the post-optimality analysis, it may contain several different parts. For example, if we want to, as we've seen earlier, we can read from the first row of the simplex tabular about the shadow prices, and this helps us to make appropriate decisions of organizational resources between activities under study and other important activities. On the other hand, if we actually want to change some of the constraints or the coefficients in our model, we can conduct the sensitivity analysis. And this is what we are going to talk about today. So for a linear programming problem in its standard form, we say that the work of sensitivity analysis is to decide when the parameters b, c, or aij change, the optimal solution will change. How does the optimal solution change when the parameters change? And this, when the coefficient changes, the optimal solution or the model will change. This is called the coefficient sensitivity analysis. On the other hand, practically, we may also add new variables or add some new constraints. And the new variables or new constraints will also affect the optimal solution. And then how will the optimal solution in this case? And in this case, we call this the structural sensitivity analysis. In this lecture, we first look at the coefficient sensitivity analysis. The basic idea to consider how any changes in the original model would change the numbers in the final simplex tabular. After making a few simple calculations to write this tabular, we can check easily whether the original optimal BF solution is now non-optimal or infeasible. If so, this solution will be used as the initial basic solution to restart the simplex method or the dual simplex method to find the new optimal solution if desired. If the changes in the model are not major, only a very few iterations should be required to reach the new optimal solution from the advanced initial basic solution. On the other hand, changing parameter values in the primal problem also changes the corresponding values in the dual problem. Therefore, we can choose which problem to use to investigate each change. Because of the primal-dual relationship, it is very easy to move back and forth between the two problems as desired, so we can choose at our convenience. For example, given a linear problem in its standard form, if we change several of its parameters, for example, in the objective function, we change the coefficient of x1 to 4, and then in the constraints, we change the coefficient here to a 2, and then the constant terms also changed. So in this case, when we change several of these parameters, how will our optimal solution change? In order to solve this problem, we first recall that in our simplex method, the final tabular is consisted by several parts. The equation 0 or the row 0 consists of the values of our objective function and the values of the basic and non-basic variables in the dual problem. So reading from row 0, we have the surplus variables, the values of the variables in the dual problem, and then the value of the objective function. In the middle of our simplex tabular, the other rows consist of, first, the basic variables and their values, and then the matrix formed by the slack variables. And all these are denoted as A star, which is the matrix of the decision variables, and then S star, the matrix of the slack variables, and then B star, the final right side in the simplex tabular. And then, with all this notation introduced, we say that we consider the change of parameters case by case. First, we consider if the only change in the model is a change in the BI, the right side of the constant terms. Suppose that the only change in the current model are that one or more of the BI parameters have been changed. Let B bar denote the new vector. Then the only resulting changes in the final simplex tabular are in the right side column. For example, in this our original model, let's consider all other parts still remain the same, and the only change here is that we change the second constraint from less than or equal to 12 to less than or equal to 24. This may be because now we have more materials to deal with, and then we have such changes. So then, in the new simplex tabular, as we mentioned, the only change in the final simplex tabular will be the right side column. After we change the vector from 4, 12, 18 to 4, 24, 18, then in the new simplex tabular, our right side will be changed to this pattern, while the objective function is changed to y star times b bar, where y star is just the values of the slack variables. And then b star, the new right side, will be s star, the matrix of the slack variables, times b bar, the new column vector of b's. Therefore, both the conversion to proper form from Gaussian elimination and the optimal test steps of the general procedure can be skipped. If S star B is bigger than or equal to 0, then the current solution is still feasible. Thus, basic solution set will remain the same. Only their values and the z-value will change. On the other hand, if S star B bigger than or equal to 0 does not hold, at least for one of the constraints, then the current solution is not feasible, so we need to apply dual simplex method to find a new optimal solution. Now let's look at an example how this actually works. For example, as we saw earlier, the only difference for our model is when we change the parameter 12 to a 24 on the right side of the constraint. That means our column vector is changed to this new form. And then, if we apply simplex method correctly on our original form, we can obtain our final simplex tabular as this. So we'll skip the details of the calculation, and interested audience can work it out themselves. So after we obtain this final simplex tabular, we say that the only difference when we build up the new simplex tabular is based on our new column vector, the right side. But we're not going to replace the right-hand side by this new vector directly, because according to our rules, the new right side will be obtained by these formulas. Z star, the new objective function, is y star times b. What is y star? Y star is simply the values of the slack variables, or the complementary basic solutions in the dual problem. So starting from x3, so 0, 3 halves, and 1, times b bar, the new column vector, 4, 24, 18, and then we can find out a new value. And then the new right side, the constant terms, will be calculated by S star, which is the matrix of the slack variables, times b bar. So the matrix corresponding to the slack variables are just below here from x3 to x5, a 3 by 3 matrix. And use this matrix times our new column vector b of 4, 24, 18 and obtain a new column vector. So this new column vector will be the new values of our basic variables in the final simplex tabular after we change the parameter bi. So now with the new objective function and new right side ready, we're going to replace in the final simplex tabular the right side by the new columns z and then this new b. So after replacing the right side, we check whether this table is still optimal. So we need to check two parts. The first part is to check whether equation 0 is optimal. That means if all the coefficients in equation 0 satisfy the non-negativity constraint. Yes, there is no negative coefficients. So the optimality test is passed. Second, we need to check whether the solution is feasible. That is, whether all the basic variables are non-negative. So if we read the right-hand side, we can see that there is actually one basic variable, x1, that is negative. So in this case, the solution is not feasible. So since there is one negative value on the right side, but the first equation 0 has all non-negative coefficients, we say we have to apply the dual simplex method to obtain an optimal solution. So apply the dual simplex method. This is the row we deal with. So x1 is leaving, and then apply the minimum ratio test. Actually, here, since we only have one negative coefficient, so this is our only choice. So choose this column, and then x4 is entering. So then apply Gaussian elimination. If we apply that properly, we can obtain a new simplex tabula. And then in this tabula, we can again check the equation 0 has all coefficients non-negative. Right side has all the basic variables non-negative. So this solution is feasible and it passed optimality test. So this is an optimal solution after we change the variable or the value of B2 from 12 to 24. So in this case, we say we can again obtain the new optimal solution and then the new value of our objective function. Next, we can consider another problem about how large an increase of B can be so that the basic solution can still return feasible. That is, the final optimal tabula is still optimal. Well, we say that the only change for our new simplex tabula is the right side. So as long as the right side is bigger than or equal to 0, it's feasible. So the new right side B star is S star times B bar. So the change of B2 is just a small change, delta B2, that needs to be determined. And then if we simply do the matrix multiplication, we can obtain a column matrix. We say that this column vector has to be bigger than or equal to 0 so that all the basic solutions in the final simplex tabula are still non-negative. So solve all these inequalities, we can see that actually after solving all the inequalities, we can find out the range of delta B such that our optimal solution is still optimal in the new setup. So in this case, we say our B2 has to be between 6 and 18. Within this change, if we change B2 from 12 to a value in this range, we say we don't need to do anything to our simplex tabula. Our original optimal solution will still remain optimal. So this is first, we discuss what happens if a parameter bi is changed. Second, we consider the case if we change the coefficient of a non-basic variable. Consider a particular variable xj that is non-basic variable in the optimal solution, shown by the final simplex tabula. If the only change in the current model is that one or more of the coefficients of this variable, ci, which is the coefficient of xj in the objective function, or a's have been changed. Let cj bar and aij bar denote the new values of these parameters, and let aj denote the vector containing all the changed coefficients. And then we have this replacement. In the revised model, for example, if we have this linear programming problem with what we have discussed earlier, this is 24. And then we change the coefficients of x1 in both the objective function and in the constraints. So change 3 to a 4, and then change this 3 to a 2. So after making these changes, we say that the coefficient of xj in our new final equation 0 will be zj star minus cj bar, which is computed by y star, again, the values of the slack variables, times aj bar, the new coefficient matrix, minus cj bar. And then the coefficient of xj in the final row 1 to m will be aj star calculated by S star times AJ bar. So in our final simplex tabular, we simply again do these substitutions and then check our solution is still feasible or not, still optimal or not. For example, in this case, we say the only change in the objective function is this 3, so our C1 bar is equal to 4, is changed to 4. And then our column vector is changed from 1, 0, 3 to 1, 0, 2. So this is our new column vector. With this calculated, we say then the coefficient of xj in our final equation 0 is calculated by this formula. So we simply do the calculation and we say the coefficient in our new simplex tabular will be 1. And then if we calculate it correctly, the new column vector corresponding to x1 in our new simplex tabular will be 1, 1, negative 2. So again, we start from our final simplex tabular from the original problem. And then in this problem, this column is the old column vector coefficients of x1 corresponding to the old problem. But now after change of the parameters ci's and ai's, we say that we're going to replace the coefficient of x1 in the objective function by 1. And then the rest of the coefficients in the constraints are replaced by 1, 1, negative 2. So after doing this substitution, we see that this is our new simplex tabular after we do these minor changes. So after we change the parameters c's and a's, we obtain this new simplex tabular. By looking at this tabular, we can see that, again, equation 0 has all the coefficients non-negative. Also, on the right side, all the coefficients are non-negative. So this solution passed the optimality test and is feasible as well. So in this case, our original optimal solution is still an optimal solution. And then the objective function, our basic BF solution, still remain the same. So in this case, because of the fact that the coefficient of x1 in our objective function is bigger than 0, the optimality test is passed for the current optimal solution. And then we do not need to do any changes to our model here. Okay, so duality theory provides a very convenient way of checking these changes. If the complementary basic solution y star in the dual problem still satisfies the signal dual constraint that has changed, then the original optimal solution in the primal problem remains optimal as it is. Conversely, if y star violates this dual constraint, then this primal solution is no longer optimal. If the optimal solution has changed and we wish to find a new one, we can do so rather easily. To use duality theory to draw the same conclusion, observe that the changes in Ci and A leads to the single revised constraint for the dual problem. Both this revised constraint and the current y star are shown below. First, we have y1 star 0, y2 star 0, y3 star 5/2 reading from the final simplex tabular. And then we say that the new constraint in the dual problem will change from y1 plus 3y3 bigger than or equal to 3 to y1 plus 2y3 bigger than or equal to 4. And in this case, actually, the new values of our yi's satisfy this constraint. So our solution is still optimal. Next, we consider with this problem, when we change the coefficients of xi, how much we can change for c's or a's so that a solution still remains optimal. So the solution still remains optimal when all the allowable range Ci can be calculated. As we can see from the example, as long as Cj star minus Cj bar is bigger than or equal to 0, it passed optimality test. So the only thing we need to care about is Cj is less than or equal to y star A1, which is calculated as 7/1/2. So as long as C1 is less than or equal to 15/2, the our optimal solution is still optimal in our new simplex tabular. So in conclusion, we say that if we change in our original final simplex tabular, we have all these changes. We can change the coefficient of the objective function or the coefficient matrix of one variable in the constraints. And then we can, in our new final simplex tabular, all we are going to do is to replace the old coefficient of the variable in the objective function or in the coefficient matrix by these things. And after this computation, we substitute them into our new simplex tabular and check whether it passed optimality test. And if yes, this is an optimal solution. If no, we just go through another iteration to find a better BF solution.